Let's finish up that electrohydrodynamic pump example. So remember, ultimately we were looking to find the pressure on the pump. So I've copied our schematic of the pump here from the previous video, as well as our end result of our voltage expression. And so remember, this voltage expression can be used to find the voltage anywhere between Z equals 0 and Z equals D. And we said that it's not going to depend on our rho or our phi. But ultimately, if we're trying to find pressure, we want to note that our pressure is equal to force over area. And note that I'm using rho for pressure to agree with the book's notation, because apparently the book thought that we weren't using rho for enough other parameters. So going back to a couple videos ago, we said that our force can be related to our electric field via QE. So we have QE over area. And now ultimately we want to bring this back to our to our voltage. So we can say this is Q, and then our electric field is negative the gradient of V. So now we sort of have a game plan in terms of how we're going to find that pressure. So the first thing we want to do is take the negative gradient of our electric field. So we have E, which is equal to negative gradient of V. And so remember, in general, that's going to be negative partial of V with respect to rho in our rho direction, minus 1 over rho, partial of V with respect to phi in our phi direction, and finally minus the partial of V with respect to Z in our Z direction. But again, our V is only dependent on Z, so these first two terms are going to go to 0, and we're only going to focus on that last term. So if we take that partial derivative with respect to Z, what we're going to get is we have a rho naught over epsilon. So we have the negative sign is going to cancel out with our negative sign here. So we have just the rho naught over epsilon, because the 2 from the Z squared comes down and cancels out that over 2. And then we just have Z. And I'm going to simplify this. So remember, in our previous video, we had integration constants. This was A and this was B. So I'm going to, for now, just say this is minus A, and that's in our Z direction. And so, of course, we could expand that out and we could include that A. So let me just actually go ahead and write that for completeness. So we have our rho naught over epsilon times Z minus rho naught D divided by 2 epsilon plus V naught over D, and all of that is in our Z direction. Okay, so now we have an expression for our electric field. And so as we might have expected, we see that this is also only dependent on Z. All right, so from there, what we want to do is we want to find our force. So we can find force by multiplying that by Q. All right, so let's come down here and we can say that in general, we know our force is equal to Q times E. Well, what is our Q in this case? So we need to go back and consider the fact that we have this uniform charge density. And so I've not written it here, but that was 25 millicoulombs per square meter. So 25 millicoulombs per square meter. And so what we want to do then is that's a volume charge density. So we need to integrate over the volume. So we say our charge is going to be the integral over the volume of rho naught times E dV. So this rho naught being a constant, we can pull that out of the integral. So now we have rho naught out front of our integral. And because our E is in the integral, but it's only dependent on Z, so we can sort of break that integral into two parts. So we have sort of an integral over, we can think of it as an integral over rho and an integral over phi. And then our integral over Z is where we're going to leave our electric field in. Well, this double integral here is just the integral over our cross-sectional area. And so we know that that integral over our cross-sectional area is just going to be S, as we've defined up here. So coming back to this expression then, we can say this is the integral over S. So let me change this to match that notation. So this is the integral over S times ds. And then we have our third dimension integral from Z equals 0 to D of our electric field dz. And again, that's because our electric field, as we see up here, is only dependent on Z. So from there we can integrate and get our force. So we see force is equal to rho naught. This integral becomes just our surface area S. And if we integrate that E expression, we have rho naught over 2 epsilon. So our over 2 has come back. We have z squared again. And now we have our rho naught d over 2 epsilon z. So we're basically just going back to our v expression essentially. So we have v naught over d also multiplied by z. And now we're evaluating this between z equals 0 and z equals d. And so remember, all of this is in our z direction. Okay, so what we're going to see is if we evaluate at z, of course, all of those terms are going to go away. So we're going to have our force is equal to rho naught s times. So we're going to evaluate at d. So we have rho naught d squared over 2 epsilon. And we're going to subtract from that. We have here rho naught d times d, which is also going to give us d squared over 2 times epsilon plus our v naught, because we have d divided by d, which will cancel out. And so we have our v naught, and then as I said, when we evaluate at 0, that just gives us 0. Again, still in our z direction. And so what we can see is that these two terms here are going to cancel out, and we're left with just our rho naught s times v naught in our z direction. Now we go back to that definition of pressure. We said our pressure was force over area. So we need to divide that force by our cross-sectional area, S. So we have our pressure is equal to F divided by S, which we can see is just going to be rho naught V naught. And so we plug in our values. So this is going to be our 25 times 10 to the minus 3rd coulombs per meter. And our volts, we had 22 kilovolts. So I don't think I had copied that in this video, but that was given in the previous video. Our V out was 22 kilovolts. And so that gives us a final answer for our pressure of 550 Newton per meter squared. And so if anybody has questions about how those units work out, feel free to let me know, and we can go through a detailed dimensional analysis. So as I said, we're not going to spend too much time getting into more complicated examples where we have dependence on multiple directions of our voltage. But for more simple examples as well as some more complicated ones, you can look at page 231 to 249 in the textbook. And so all of these examples deal with applying Poisson's and Laplace's equation. So Poisson and Laplace equations. And so of course, as you're working through those, if you have any questions or you run into issues, definitely let me know.